Imagine a power source that never runs out, harnessing the fundamental interaction of fresh and salt water. This is the promise of osmotic power, or blue energy, a groundbreaking renewable technology poised to revolutionize our energy landscape. It captures the immense energy released when waters of differing salinity mix, converting it into clean electricity. For scientists and engineers, this field presents a fascinating convergence of fluid dynamics, materials science, and electrochemistry, offering a sustainable pathway to a decarbonized future. Osmotic power leverages the natural phenomenon of osmosis, where solvent molecules move across a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. In the context of blue energy, this involves the controlled mixing of freshwater, low salt concentration, and saltwater, high salt concentration, typically at river estuaries. The chemical potential difference between these two solutions drives the process. Two primary technologies dominate osmotic power research: pressure-retarded osmosis, PRO, and reverse electrodialysis, RED. PRO systems use the osmotic pressure difference to drive water through a membrane, generating a pressurized stream that can spin a turbine. RED systems, conversely, use ion-selective membranes to create an electrochemical potential difference, generating an electric current directly. Both approaches aim to efficiently convert this natural energy gradient into usable electrical power, presenting unique engineering challenges and opportunities. The efficiency and economic viability of osmotic power systems are critically dependent on the performance of their semi-permeable membranes. These membranes must exhibit high selectivity for ions, allowing water or specific ions to pass while blocking others, and possess high permeability to maximize power density. Recent advancements in materials, science, and nanotechnology are driving unprecedented improvements in membrane design. French startup Switch Energy is at the forefront with its ionic nano-osmotic diffusion, INOD technology. This innovative approach utilizes biomaterial membranes, drawing inspiration from biological systems known for their highly efficient transport mechanisms. The key lies in advanced patented nanotube technology, creating pores with an incredibly precise diameter of just 10 nanometers. This nanoscale precision is crucial for optimizing ion transport. These biomimetic membranes offer superior ion mobility compared to conventional synthetic materials. The specific surface chemistry and structural integrity of the biomaterials, combined with the uniform, ultra-small pore size of the nanotubes, facilitate rapid and selective ion passage. This design minimizes resistance to ion flow while maintaining high selectivity, directly translating to higher power output and improved energy conversion efficiency. Research into these novel materials involves complex characterization techniques and computational modeling to understand their unique transport properties. Recent research has yielded new semi-permeable membranes capable of significantly boosting osmotic energy output. These membranes have demonstrated a power density more than double that of commercial membranes in laboratory settings, specifically in estuarine conditions. This leap in performance is attributed to novel membrane architectures and material compositions that optimize both water flux and ion selectivity. The design principles often involve creating highly porous yet selective structures, sometimes incorporating thin film composite (TFC) designs with optimized active layers. Maintaining this enhanced performance over long-term operation is a critical engineering challenge, requiring membranes to withstand fouling, compaction, and chemical degradation. Researchers are employing advanced surface modification techniques and robust support layers to ensure durability and consistent output, addressing the practical demands of continuous power generation. At École Polytechnique Fédérale de Lausanne, EPFL, researchers have explored the potential of two-dimensional, 2D materials for osmotic power. Their work on specialized membranes made of molybdenum disulfide, MOS2, measuring just 3 atoms in thickness, has reportedly generated unprecedented yields. The unique atomic structure of MOS2, with its layered arrangement, allows for the creation of ultra-thin membranes with precisely controlled nanopores. The extreme thinness of MOS2 membranes minimizes the diffusion path for ions, leading to exceptionally high ion flux. Furthermore, the intrinsic properties of 2D materials, such as their high surface area and tunable surface chemistry, offer opportunities for optimizing ion selectivity. This research delves into the fundamental physics of ion transport at the nanoscale and the engineering challenges of fabricating and scaling up such atomically precise structures. The potential for high power density from these materials opens new avenues for compact and efficient osmotic power systems. Translating laboratory breakthroughs into grid-scale power generation requires significant engineering effort, meticulous design, and rigorous testing. Pilot plants serve as crucial intermediaries, demonstrating the viability of new technologies under real-world conditions and providing invaluable data for optimization and scaling. Switch Energy's Osmotic pilot plant, operational at the end of 2024, represents a significant milestone for osmotic power. Strategically located at the confluence of the Rhone River and the Mediterranean Sea, it capitalizes on a naturally abundant and consistent source of freshwater and saltwater. The site selection is critical, as it ensures a stable salinity gradient and sufficient water flow for continuous operation. The Osmotic plant aims to gradually scale up production, targeting an ambitious long-term capacity of 500 megawatts. This capacity could power over 1.5 million households, demonstrating the potential for osmotic power to contribute substantially to national energy grids. The engineering challenges involve designing robust intake and outflow systems, optimizing membrane stack configurations, managing biofouling and scaling, and integrating the power generation unit with the existing electrical infrastructure. Data collected from Osmotic will be vital for refining system design, predicting performance, and assessing economic viability at larger scales. Securing investment and developing clear commercialization pathways are essential for any emerging renewable energy technology. The valley of death between research and market deployment requires substantial capital, strategic partnerships, and a compelling economic case. Switch Energy's success in securing €5.2 million in 2021 underscores growing investor confidence in osmotic power. This funding was earmarked for initiating the industrialization phase and developing a first full-scale prototype. Industrialization involves transitioning from bespoke laboratory setups to standardized, manufacturable components and systems. This includes optimizing manufacturing processes for membranes, designing modular power generation units, and establishing supply chains for critical materials. The development of a full-scale prototype is a critical step, allowing for comprehensive testing of system integration, performance under varying environmental conditions, and long-term reliability. This phase also involves detailed techno-economic analyses to refine cost projections and identify market entry strategies, paving the way for broader commercial adoption. Redstack, a Dutch company, is a key player in the commercialization of osmotic power, specifically focusing on reverse electrodialysis, RED technology. Unlike PRO, which relies on hydraulic pressure, RED directly generates electricity by selectively transporting ions across alternating cation and anion exchange membranes. This creates an electrochemical potential difference, similar to a battery. Redstack's work involves optimizing Redstack design, improving membrane durability and selectivity, and developing efficient power conversion systems. Commercialization efforts for RED technology focus on applications where consistent baseload power is needed, such as coastal industrial facilities or remote communities. The challenges include reducing capital costs per kilowatt, improving stack efficiency, and managing membrane fouling in real-world water sources. Their focus on commercializing RED highlights the diversity of approaches within osmotic power and the ongoing efforts to make it a competitive energy source. Osmotic power offers several compelling advantages that position it as a valuable component of a diversified renewable energy portfolio. Its unique characteristics address some of the limitations of other intermittent renewable sources. Osmotic power directly advances climate action by generating clean, renewable electricity without producing greenhouse gas emissions. Unlike fossil fuel-based power plants, osmotic systems do not release carbon dioxide, sulfur dioxide, or nitrogen oxides into the atmosphere. This significantly reduces reliance on fossil fuels, contributing to global efforts to mitigate climate change and improve air quality. The life cycle assessment of osmotic power systems, from material extraction to operation, generally shows a very low carbon footprint. the primary environmental considerations revolve around the localized impact of water intake and discharge, which are carefully managed through environmental impact assessments and engineering design to minimize disruption to aquatic ecosystems. One of the most significant advantages of osmotic energy is its non-intermittent and abundant nature. Unlike solar or wind power, which are dependent on weather conditions, the salinity gradient between freshwater and saltwater is a constant and predictable phenomenon at river mouths and estuaries. This makes osmotic power a potential source of baseload electricity, providing a stable and continuous supply to the grid. The global potential for osmotic power is vast, with numerous estuaries worldwide offering suitable conditions. Research estimates suggest that the theoretical global potential could be in the terawatt range, making it a significant untapped resource. This inherent stability and predictability are highly attractive for grid operators seeking reliable power sources to balance fluctuating renewable inputs. Combining osmotic power with other renewable energy sources, such as solar PV or wind power, can create highly effective hybrid systems. This integration offers increased energy generation consistency and improved grid stability. For instance, an osmotic power plant can provide a steady baseload, while solar or wind assets can supplement power during peak demand or favorable weather conditions. Hybrid systems can leverage shared infrastructure, reducing overall capital costs and improving operational efficiency. The dispatchability of osmotic power, even if limited, can be strategically managed to complement intermittent sources, ensuring a more reliable and resilient energy supply. This synergistic approach maximizes the benefits of each technology, leading to a more robust and sustainable energy grid. While significant progress has been made, osmotic power still faces engineering and scientific challenges that present fertile ground for further research. These include improving membrane durability and fouling resistance, reducing capital costs, and optimizing system integration. Developing advanced materials that can withstand harsh aquatic environments for decades is paramount. Further research into novel membrane materials, such as metal organic frameworks, MOFs, or covalent organic frameworks, COFs, could unlock even higher efficiencies. Scaling up manufacturing processes for these advanced membranes and developing cost-effective stack designs are critical engineering challenges. Additionally, exploring the environmental impacts and benefits of large-scale osmotic power deployment, including potential effects on local ecosystems, requires ongoing scientific scrutiny. Osmotic power, or blue energy, stands as a testament to human ingenuity in harnessing nature's fundamental forces for sustainable energy. From the atomic precision of molybdenum disulfide membranes to the ambitious scale of pilot plants like Osmorone, the scientific and engineering community is rapidly advancing this promising technology. Its potential to provide continuous, clean, and abundant electricity makes it an indispensable component of our future energy mix. Are you ready to contribute to this energy revolution? Dive deeper into the research, explore collaborative opportunities, and consider how your expertise in materials, science, fluid dynamics, or electrical engineering can accelerate the deployment of osmotic power. Engage with leading research institutions and companies in this field, and help us unlock the full potential of blue energy to power a sustainable world. Your insights and innovations are crucial for transforming this scientific promise into a global energy reality. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.